Good evening, everyone. Warm welcome to the already 17th Vienna Deep Learning Meetup. We are this time for the first time at Wien Energie. Very thankful that Wien Energie hosts us tonight in this really great room here. And we have, as usual in the past times, a great number of people here in the audience and again a YouTube live stream today. So welcome also to the people who watch us online. Who are we? Actually, we're three organizers of the Vienna Deep Learning Meetup. We do this usually monthly, with a few exceptions, like we had to skip last month. Previous one was in February. And the three of us are me, Thomas Liedy from Musimap, Jan Schluter from the OFI, and Alex Schindler from the AIT and TU Wien. The two of them will present later on latest news and hot topics, which is a regular section at our meetup. If you haven't checked it out, we have on URL because it wasn't possible before. So it's just youtube.com/Vienna Deep Learning Meetup. Just quickly mentioning the agenda of today, and sorry, it's the 17th, forgot to correct it. Brief welcome from me, who will then hand over to our first speaker, Anouk Visser from Birds.ai, who made it all the way from Amsterdam to come here just for tonight's meetup for you. We are very, very happy and grateful for that. Her talk is called AI to Provide a Bird's Eye View. We're gonna hear about how drones monitor wind power plants. Then we have a few announcements and a 30-minute break where our hosts, Wien Energie, thankfully provide us with drinks and snacks, and so you can mingle and chat with other people here. Then we're gonna have our second speaker, Christoph Götz, who is the CTO of Image Biopsy Lab, and he's gonna talk about enhancing the medical expert, how to help doctors with AI. So a very interesting talk from the life science and health and medical sector. And then we're gonna do latest news and hot topics. So because the field is so dynamic, every month we try to summarize very recent developments since the last meetup. And after that, we're gonna have more time to network and discuss the topics of today or any other questions you might have around deep learning. So thanks for being here, and I'm handing over to Michael.
Hello and good evening to Wien Energie. My name is Michael Elias. I'm from Wien Energie, and believe it or believe it not, Wien Energie is interested in artificial intelligence in several years. And since more than 1.5 years, we are using algorithms to detect failures or errors in images. And yeah, I'm really proud and happy that Wien Energie is chosen to be the host of this event. And now coming straight to AI. They are located in the Netherlands, in Delft. Yeah, please welcome Anouk.
Thank you, Michael. So before I met the team at Wien Energie, there's Michael, Patrick, and Alexander. I never really thought about what it takes to actually produce energy, which is strange because this morning I was on a train from the airport in Vienna to the city and I could actually power my phone over there. Like, access to electricity is super easy. You can get it anywhere. But meeting the guys from Wien Energie, I noticed that there is so much like power plants all across Vienna. There is Spitalau, of course, and there's 65 wind turbines. There's many solar panel farms. But how do you actually make sure that these things keep producing energy? So we've been working together with Wien Energie to use artificial intelligence to make sure that every one of their assets is in top condition. So whenever we met, we were talking about wind turbines mostly. I believe, and I've never spoken to a room full of Wien Energie people, there are 65 wind turbines, all powering the city of Vienna. They don't produce enough energy for all of Vienna, but if we compare it to the city where my office is based, which is in Delft, you'll actually find that 65 wind turbines are easily enough to power that whole city. So if one of these wind turbines break down, we kind of have a problem. because this wind turbine is not generating any energy anymore, but Wien Energie will need to spend money actually to repair it. So we want to inspect these wind turbines as good as possible. And there's a lot you can see. But to actually send someone up will take a lot of time. The wind turbine has to be powered off because you don't want a guy climbing up the tower while the blades are still turning. So we came up with a solution. We call it a smart drone inspection. You can read all about it on Wien Energie's blog. And we've added a little bird's eye view theme to it. So here's how it works. We work together with a drone operator by Philip, actually. This is, by the way, a picture of the team of Birds Eye Wien Energie and Philip, the drone operator in the blue t-shirt. So Philip starts by flying his drone up and down the wind turbine. This is an actual picture, I believe, from a Wien Energie wind turbine with the drone that we use. And he collects a lot of images. For one wind turbine only, he collects 600 images. 200 images of each blade. They have a little bit of overlap because we worked on a flight protocol together. And all these images get uploaded to our cloud platform. So 600 images for one wind turbine. You don't actually want to go through all of these images manually, because that would take a lot of time. Imagine yourself clicking through all these images, 65 times 600 wind turbines for an inspection. That's not going to save us any time or money or give us any overview. So what we do is we use artificial intelligence. Oh, my animations are gone. We use artificial intelligence to actually find defects in all of these images. So probably it will select this image as being a bad example, and it will just skip over these images. And it creates a nice little inspection report. So over there you can see on the blade, like orange patches, you should probably take an action. Yellow, maybe next year. And blue or gray if nothing is wrong. Now what we're trying to do at Bird's Eye is to create a bird's eye view of the health of the wind turbine over time. So we can actually show them that, you know, maybe today it looks okay-ish, but in the future, and the AI can actually help us predict that, a sort of innocent defect will evolve into a much more serious problem. So we do all of this, the drone inspection, creating of a single inspection report, and tracking the changes over time to give the people at Wien Energie a bird's eye view of all of their wind turbines, and maybe something more, but we'll come to that later. So, now they've got an overview of how they're doing, and they have a lot of advantages. So instead of having to respond to unexpected outages, they can actually spend time in thinking about expanding their network. They have a lot more time on their hands. They can work on the energy transition. I was at the tour today, and I learned that in 2030, I think 40% of all power used by Vienna should be coming from renewable sources. Now, it becomes a lot easier if you have a bird's eye view of how all these power plants are doing, if you can do that automatically. So, today I'll be talking about how we do that. As a company, we're doing it automatically, so we could probably take on all the 350,000 wind turbines in the world. But we're starting small, we're starting in Europe, and especially in Vienna. This is my team. Michael may have introduced us already. I'm actually one of the 3 co-founders and the CTO, so a lot of the work I will be presenting on AI has been done by me. We've been growing our team rapidly, so there's a guy working on solar panels in parallel now as well, because we are not just stopping at wind turbines. Because Wien Energie also has solar panels, there's spietelau, which is chimneys, and they all need to be inspected every year. But also there's many other things that we might give a bird's eye view of. You can think of even bigger sea vessels, or aircraft, or bridges, which can all be inspected easily by a drone and by AI to actually inspect the images. But as a company, and especially as a small startup, you kind of need to focus. So we're gonna take a deep dive into wind turbines now. But just a little bit of background on the company, because I say we can generalize. We actually started out with crops. We started out in the agriculture markets, where where farmers want to counter crops to sort of know how much they can sell and where they need to maybe put a little bit of fertilizer or water. Now, there's a few things as a data scientist you notice when you look at a field of crops. There's only very small variability among all the different crops. They sort of look the same. It's easy for a human to actually go in and draw little boxes around all the crops. There's something about the colors, like it's all shades of green, sort of. So we thought, let's just, solve this with a nice object detector. And I'm going to pause here for a little bit. I had some assumptions about the audience, but maybe we can do a show of hands. Like who's in the computer vision / deep learning space? Oh, good. I'm glad. Who doesn't know what a convolutional neural network is? Fantastic. Great. All right. So let's just jump right in. To solve the problem of crop counting, we used fast RCNN, which worked quite well. So fast RCNN is a convolutional neural network that classifies regions of interest. So we use some random object proposal system. They've gone out of style already to generate a number of regions of interest. Then there's some convolution layers. You take the convolutional feature map, you pass it through fully connected layers, and you get a nice little classification output that you can use to determine if something is a crop, yes or no. So FastRCNN, I think, came out in, what was it? Around the time that I graduated, so it must be like 2013-ish. It's printed over there, 2015, even sooner. But luckily, like, innovation doesn't stand still, and we were gifted the beauty of faster RCNN, where we can completely get rid of the object proposal system. So now faster RCNN actually promises us to, in one go, select the regions of interest, but also do the classification. Now, I don't know how many of you have used faster RCNN? Better. So faster RCNN works with this anchor generation system, where on a convolutional feature map, you're going to place like 3 different scales times 3 different ratios of boxes on a convolutional image map. So you're like, you lose a lot of resolution. And then it's going to classify these boxes. So what you see is that in agriculture, the crops can be very small, and it becomes really hard to accurately localize these things. Because as it turns out, faster RCNN isn't actually able to generalize over different object ratios and different object sizes. There have been a lot of papers about this, and some of the solutions for us in agriculture was to sort of leverage the fact that crops are often in rows and columns, and adds all sorts of information. We know that they're square, etc. So by doing that, we were actually able to use faster RCNN. And we were thinking, we're an AI company, so we solved this for crops, we can go to wind turbines. Not as quickly. So when I first started to think about what it takes to do defect detection on wind turbines, I was expecting images like this, where you have a nice wind turbine blade, and there's like a very clear defect on top of them. I've actually blown it up a lot to show you what it actually looks like, because you can hardly see it. This is what we call, and we've been talking with experts from Wien Energie, this is what we call a local damage / dirt level 1. And it turns out that most of the damages are actually local damage dirt level 1. It also turns out that you actually don't care about them, but they might evolve into bigger problems later down the line, so you definitely want to know about them. This is really hard to find. But let's look at some other things. We have to detect things that are not there. There's missing components. So I've actually drawn a little dotted line of turbines. But this is called a turbulator, and it's missing. And we see that because it's supposed to be a triangle, but it's chipped off. And we were asked to detect these things. I'm not even sure what this is called, but there's supposed to be a metal strip over there. And these are things we need to detect. So this is a level 2 missing component. Now let's take a deeper dive into the local damages, because it also turns out that first of all, there's like this tiny, I don't know what it is, that's only 250 pixels, big smudges, I guess. And then there's these strangely shaped brownish things. So these pictures, they look the same size, but as you may have noticed, it's like 250 pixels, 100 pixels, 500 pixels, 250 pixels. They go from left to right, diagonals, circles, all sorts of things. So there's a lot of interclass variety, which makes this problem really hard. It's really tiny, but there's red lines running across all the damages on this particular blade. You can see really big ones like erosion, very aspect ratios in different sizes and different resolutions. So looking at the data set for wind turbines, we find that there's a couple of things that are extremely challenging in this space. First being that there's no such thing as a typical defect. So when we were doing crops, I could do the annotation boundary. So this thing is an erosion. And you can say that the erosion ends here, but the annotator chose that the erosion ends there. So what are you going to do if your algorithm tells you the erosion ends here? Is that good? Is that bad? Not quite sure. But you know how we didn't really solve for agriculture. And we applied it to wind turbines to see what happens, because no harm done. Our first tests, I think sometime fall would hope. So you might take these results with a grain of salt. Precision being the, for the people that are not into evaluation metrics, precision being the fraction actually retrieved. So you can see that we don't retrieve all of the defects. If you're a human corrector and you go through all these samples, for every 5 samples a day, you still have to find 25% of them yourself. So not ideal. We looked at ways to improve faster RCNN and to kind of try and make it work for all of these defects. But we came to the conclusion that maybe this is not the right method for us. So, so it's really hard to tweak and to actually make this work for you. So just usually you start out in computer vision with some classification. Maybe then you'll do a detection, and then maybe why faster RCNN was failing. So this is a plot of the proposal network, where we look at the recall of the region proposal network. So remember, we had the regions of interest that are going to be classified. It turns out that the intersection of union with the ground truth, so the localization capability, basically, minimal threshold will actually be only 80%, which means that 20% of the defects were not even considered. About finding defects on wind turbine blades is that it's always sort of darker. It's always being a defect, yes or no. So we started looking at this other network, a semantic segmentation network. This is a really popular network for the use in self-driving cars or semi-autonomous cars, because it can provide segmentations on the fly. So how this works is very different. So the idea comes from convolutional networks are really great at classification, but classification is a funny task where information is actually contained within a network, but it's lost the moment you do FCNs, is we actually don't attach any fully connected layers here, and we just keep the convolutional feature map. And then train a network and you pass on some indices to sort of cheat the system. You learn how to upscale your classification, basically. And that leads to, well, it's called a receptor for it, if you look at it from a brain perspective, I guess. A couple of things that you see here in the image. Excuse me for the color scheme, but green is a false negative, positive. So there's this nice thing that wasn't annotated as a defect, which is strange. Which makes me want to go back into the data. And then the blue areas I'm super excited about because they're true positives. So this looked nice, and we did some more wind turbines with the Wien Energie people. And we got more data. And then things started to look really, really great. So this is, I guess it's erosion coming out of the turbulators. And there's a few things that I really liked about this particular experiment, but it's sort of automatically learning to not classify any defects on the background. So there's a few spots where it's still thinking something in the background is a defect, but it's pretty nice that we get this functionality for still some green about the turbulators. We can deal with that later, but it does find most of the defects. If we look at this image, there's in like the downsampling in the encoder, but we find the bigger erosions and the massive defects. There may be some border disagreement here. Okay, well, I think the defect stops here. The human annotator doesn't really care as long as it finds the defects. So this looked promising. I have some numbers as well. We trained this segmentation that it doesn't actually really make a big difference what kind of defect it is. Remember, erosion is often very big and very long, and local damages are often very small. We could find all of them with reasonable precision recall. I didn't print precision here because it's kind of hard to do that for segmentation. It's fair work, because obviously there's still some problems. There's no boxes for starters. There may be holes inside the predictions. So we need to do something else to really speed up. So as part of our work on the other side, let me see if I have an example. Who of you is familiar with how to combine tile map service and deep learning? So on your average tile map server, you tile the map, well, in different resolutions. So your zoom level 0 will have the whole map of the world. And at zoom level 5, you won't lose any resolution anymore. So it so happened to be that we were already storing our images this way. Because if you see that there's a lot of, well, segmentator is saying, you would see that probably this tile would be defect, this tile would be defect, but this one would be okay. That one, well, this is one. This one would be okay. And we can wait for that. In the meantime, we'll be happy if, like, first results a couple of weeks ago, instead of doing the full prediction on all the different severities. So you can have a local damage which is level 1, but you can also have a local damage that's 2 or 3. And this level usually means the kind of action that is required. So if it's a local 3, you should definitely stop all operations immediately and fix the thing. If it's 1, you probably have to look at it again next year to monitor. I was a bit surprised. It's not that much higher than the level 1. Whereas if I look at the images, level 3 is there's a lot of confusion between 1 and 2 with our parser. And some of the images that the network thinks it confuses with the background are actually classified correctly. Average, I'm pretty sure we can detect around 70–75% of all defects. And the majority is still in the level 1, detect 70%. So this is still work in progress. Use cases, not really wind turbines, but definitely industrial inspection is a very cool thing nowadays. Medical inspection. So some of the things we want to check out is UNet. I'm not entirely sure yet what it does, but it works with skip connections to keep the rest. Very interesting thing is MOSC RCNN, which is another one in the family of the FOSS and the FOSTER RCNN. Moving on to solar panels. So this is where things get really nice, because if we look at solar panels, we don't have the same problems that we have on wind turbines. Good. So for all data scientists among you, there's nice patterns here to recognize. Sort of similar to what we saw in crops, and grids are always straight into the image, which gives us a lot of advantages in terms of finding panels and defects. So here, instead of going straight for the main event, the segmentations, we again started. So for object detection, we have a lot more panels. It's a lot less painful to annotate, and you also don't need the expertise. And these are actual results already that we got out. So even though there might be a slight shift in like rotation, we're pretty accurately able to find every panel. I have a very exciting precision recall curve for you later. This is an image that we took from the test set. We actually trained on this data set. It's a thermal image, by the way, because it's way easier to detect defects in solar panels when the image source is thermal. And this is an image from Wien Energie. On the rooftop, there's a huge solar panel field. And this is also a nice example of why we want a panel detector. Because in the end, in the inspection report, we want to present the map. Now, solar panel fields are not nice grids. On Wien Energie, there were sort of Tetris-like structures where it wasn't quite fitting. So it's also really useful to detect panels to actually automatically construct a map of the whole field. And this image wasn't in the test set, in the train set, sorry. So also if you look at the difference in temperature or the way the camera was made, you see that it's different shades of black and gray. Doesn't really matter for the detector. Oops, I already showed our precision recall curve, which is fantastic. No need to improve. Except, of course, if you start rotating the image a little bit, then you might want to go back to something like polygons instead of boxes. So this work was completed, I think, a week ago. We've slowly started to classify this. This is what a broken panel looks like. And then it's about this one. You can see the hotspots, which are squares within the panel. So as a first step, we extract the panel out of the image, and then we run it through a classifier. So this is a confusion matrix for that. Again, ground truth and prediction. This was trained on, well, not very little data, around, what is it, 800, 900 panels. We should still train it more. It might make sense to actually split up the different defects, because there's still room for improvement, definitely in precision. But so far, it's looking good. That's actually the end of what I wanted to discuss with you. I hope this makes sense in like where we're going in terms of inspection of all of these energy assets and why it's useful to use deep learning for this. Thank you. Any questions? Yeah. They're flown manually. So that's yeah. I don't have much to say about that. There's a pilot. He does a great job, and we have a nice inspection protocol, so we can control what kind of data we get in, which works.
The photos taken while the wind turbine is running, or?
No, it stopped, but like I believe if a man would climb up, it would have to be turned off for 8 hours, and with a drone, it only takes an hour, maybe even shorter.
Hi. Great results with that less training data. I'm really surprised about that. I mean, 600 images or so, it's really nothing compared to what you hear normally, what you need to train any data model. Is it because you can use pre-trained images, pre-trained models, which have some more superficial layers, which are already recognizing areas and so on, and you are just putting your magic on it?
For some of the models, we did initialize from ImageNet, but only the first couple of layers make sense, where there's all the low-level features. Some models were actually trained from scratch, so the segmentation work you saw in the wind turbines, which also really surprised me, they're trained completely from scratch.
It's amazing.
Because most of the information you get from ImageNet, it's very different. Like these are not horses and cats. These.
But it's really great. I mean, 600 images is nothing for data. And one question, how did you prepare the data? How did you annotate the images?
So this is a thing that we do in collaboration with Wien Energie, because we don't know anything about all the different defect levels. We build our own tool, Birds.ai view, of course, where we can draw polygons. And we're building in some not quite ready for production AI to speed up the process. So we do a proposal to the annotator. The annotator can go yes or no. So that's also why we do the tile classifier now, instead of going straight for polygons. But nothing special there, and there's no pre-processing or anything unusual. It's just we started doing polygons really early on because we know that's where we're moving to. We're not even always using them. You can always make a box or just a label out of that.
Do we have more questions? Yeah, here. Over there.
Hi, I don't understand the use case very well, so correct me if I'm saying something stupid, but if the drone was to fly automatically, couldn't you just use some attention-based mechanism to decide where to fly and check where parts could be missing? Because I guess a wind turbine always looks the same and should always have the same parts. And if I define, like, check this region, and it can just check, oh, maybe there's something wrong and fly closer, you know, on the fly, just deciding that?
On the flight would be nice, but it's not necessary. So what we do right now is we do the analysis offline. It could be cool in the future to run this on a drone and to instantly on the spot decide if a repair is needed. We do, however, find that different wind turbines look very, well, different in shape and size and what kind of components are supposed to be there.
Oh,
The use case in this case is that we use the drone to only collect the images. Then all that data is uploaded to our platform. We analyze that data and then we create a visualization. So there's a blade where the first blade is colored red and the other one is yellow. So the inspectors at Wien Energie can really instantly glance how well their whole wind farm is doing, but they can also zoom into individual wind turbines, individual blades, and individual defects.
Okay, yeah, it was just more about like the data collection part. Because
Yeah.
if you think that there's something wrong, just flying closer on the fly. But I guess, yeah, I get it. Thank you.
Yeah.
Thanks. There was another question.
Hi, just another question on the low image number. You had 600 images. Did you use any kind of data augmentation during the process? If yes, which? And also, what was the loss function you used for the segmentation? Because what we found out is that if you just use accuracy as a measurement, that doesn't work very well on very small patches, which you also had. So, what was your solution to that?
Right. So first question about data augmentation. In all the different experiments, we used different data augmentation methods. Foster RCNN didn't work well on wind turbines at all when we didn't subtract the mean image explicitly before we passed it in. So there's a couple of strange behaviors for some of the networks, especially when it comes to wind turbines. For the segmentation network, we use sort of standard transforms and all that to really upgrade the amount of data that we had. In terms of loss functions, I'm not sure, but I do remember that for SegNet, we build our own loss function because it doesn't really pay off to look at pixel accuracy, because only, under a percentage of pixels are not part of the background, are actually defect. But pixel accuracy is a very unfortunate metric because it just looks at the total number of pixels being classified correctly. If everything is background, then it becomes really easy to say background. So we did make some adjustments there. We didn't come up with a name for this loss function. But yeah, if you want to know more about that, maybe we can chat later. I'm not entirely sure if I have it at the top of my head, but I agree. This was necessary to make it all work.
Any more questions? Yes, another one here.
I have two, if I'm allowed. How much of that is already in productive use?
The solar panels is in productive use, so whenever we get a new solar panel field, we'll just put it in the system and use it as a pre-annotation. For wind turbines, it's still more experimental, but we're slowly starting to replace part of the annotation system by these predictions.
And for the wind turbines, do you need more images to go to productive stage, or what do you need more?
We need to, so the tau classifier that I presented is a couple of weeks old. We need to really upgrade the precision. For most of the classes, the recall is okay because we'll still have a human corrector going through it. But the precision was quite low, as you could see in the confusion matrix. So there's still some issues to solve there, which is also part of the way we transform a polygon to a tau and all sorts of things. We need to take care of that and get real good, clear results without noise in the data.
Okay, thanks.
Yeah.
So, thanks a lot, Anouk.
Thank you.
Let's thank Anouk for this great talk. Wonderful presentation. Yep. Before we go into the break, we do our announcements. We have two kinds of announcements. One is about job openings, and the other one is about upcoming events. May I have Andreas Burner coming up here? He's right over here. We're going to just switch again.
Okay, so I start. Thank you, Tom, for allowing me to introduce or tell you something about the job opening here in Vienna. So my name is Andreas Börner. I'm from SmartStream Technologies. SmartStream is a company in the financial technology domain. Actually we are looking for machine learning, deep learning data scientists. So can I switch here? Okay. Okay, so maybe some words about what we offer. Yeah, so SmartStream is in the fintech space. It's quite a big software vendor based in Vienna. If you're not familiar with fintech, you would not know SmartStream, but they are big. Yeah, they have 1,500 customers worldwide, many of the top banks. And the people in the banks and financial institutes, they see a lot of need for machine learning in that area. So basically, SmartStream is opening a new lab in Vienna, researching on many word2vec and many domains. Yeah, so it's about applying the standard machine learning concepts to the financial world. There are not so many that do that right now. So basically, if you are familiar with machine learning, deep learning, typical frameworks, if you bring with you a certain curiosity and are not allergic to financial data, then please talk to me in the break or contact us via email. So I'm happy to hear from you. Thank you very much.
Thank you, Andreas. Okay, now about the upcoming events. There are two exciting ones. One is this one. But it's more about smart automation and robotics. It's organized by the Mobile World Congress that is usually normally in Barcelona, but this one is in Munich, 19th to 22nd of June. Calling startups to join and also exhibit there. There is a post on our discussion board on our meetup group online. So this is a good reminder. You might want to check out also the discussion forum, or called discussion board, on meetup.com in our Vienna Deep Learning Meetup group, where we also do job announcements and other announcements. It's actually a platform for knowledge exchange. Also a reminder that we have a wiki there. In German, it's just called Seiten, where we collected for a time some resources also to get started in deep learning, in case you just got started. May I ask at this point actually, who is at our meetup for the first time? Okay, I would say about a third, yeah. Who has just started to do deep learning with some resources, and of course also use this meetup to interact and chat with the other people about their experiences. Before the break, this is our big event coming up in May 7th. We announced it a couple of times that we're going to organize something around ethics and bias in AI and deep learning, and we had to shift it a couple of times, but this time it's really happening. May 7th in the deep learning group, but if you have missed it, please check it out soon. It's in our regular events, and also it has a website on its own, aiethics.cisvienna.com. This wonderful discussion of ethics and bias. Join us. We have two keynote speakers, and 5 panelists, and an evening full of discussion of these important topics. Yeah, to tackle it from the Center of Informatics and Society of the TU Wien, and therefore it's also happening there. We have 300 places, but I checked this morning, 200 are already registered. So if you want to join, please don't hesitate too long to register. But yeah, we are really looking forward to this event. It's kind of a special edition of our Vienna Deep Learning Meetup, and it's in exactly 2 weeks from today. Thanks. We're doing the break now, and we'll be back in half an hour.